So now we're entering into vector addition. Okay. The good news is that what you're going to learn today, you kind of already know. Okay. We're going to be going over, at least for the first part, the addition of collinear vectors, which collinear vectors are things like forward and backward, okay, right and left, right? You basically just have opposing directions, positive and negative. Right? Then we'll start looking at perpendicular vectors, where something goes north and then turns and goes east, right? But you'd always have a right angle. And then from there, we'll move into vectors that are not collinear or not perpendicular, okay, and what we have to do in order to add those. Okay. The good news is that the fundamentals are the same no matter which kind you're going over. Okay. All right, so first thing is we need to understand what collinear vectors are. Okay, collinear means they share a line, so they are on the same plane. Okay, that would be again right and left. Okay, forward, backward, that kind of thing. Okay, all vectors are added by placing them tail to head. So we're going to look at how we draw vector diagrams today, okay, and we'll show you what we mean by placing the vectors tail to head. Essentially, we're placing the tail of the second vector on the head of the first. Okay. Also understand, and this is something we've gone over 100 times already, vector quantities have magnitude and direction. Please don't forget to put direction on after you do all the work to find it. And then lastly, understand all vector quantities are added in the same way. Okay, displacement, velocity, acceleration, all that. It doesn't matter what we're adding. Force, if it's a vector quantity, we add them in the same way. The only thing that's different is at the end, we put on different units. Okay, so if I added 2 displacement vectors, my end units would be meters. If I added 2 acceleration vectors, my end units would be meters per second squared. If I added 2 forces, my end units would be newtons. Okay, but the fundamentals of doing it is exactly the same no matter what vector quantity I'm adding. Right. Okay, so with vectors, here's how we draw them. Okay, any vector quantity is represented by an arrow. The length of the arrow represents the magnitude of that vector. Okay, so if I was drawing a 2 kilometer long vector, like you see there on the screen, okay, that I would draw it that length, and if I was drawing a 1 kilometer vector, I would only draw it to be half as long. Now I don't have to measure out the scale and do all of that, okay? Like you don't have time to do that, and I don't expect that you draw everything to scale. Try to do your best to represent scale as best you can. All right. So if you have one vector that's supposed to be half as long as the other, make sure it's about half as long. Don't draw it like this much shorter, okay? Because it'll really start to throw off your diagrams. All right. So you don't have to draw it exactly to scale, but try to represent the scale as best you can. Okay, so the length of the arrow in all vectors represents the magnitude, and okay, the direction the arrow is pointing represents the direction of the vector. Okay, so in this case, this vector here is 30 degrees north of east. Okay, now why don't I just say 30 degrees northeast? Why did I say north of east? Are they the same or different? Okay, they're different, and why are they different? Exactly. Okay, 45 degrees north of east is northeast. Okay, it's also 45 degrees east of north. It's right in the middle. Okay, this is only 30 degrees north from due east. Okay, if I just say 30 degrees northeast, there are 2 of those. There's this one that's 30 degrees north of east, and then there's this one that's 30 degrees east of north. And those don't point the same way. Okay. Yes, sure, they point to the same sector of the compass, but they're not pointing the same way. All right, so we always have to write things as east or north of one of the primary compass directions. Okay, how do I determine that? Well, okay, when I draw my vector and I put in the little angle arc here, okay, whatever compass direction that arc touches is what I'm measuring from. Okay, so this moved north of east. Okay, so whatever direction the angle arc touches, that'll be your of direction. So that's of north of east. Okay, if I had a vector that was pointing, let's say this way, and I drew it like this, so it was 40 degrees, okay, that would be 40 degrees which way? West of north. Okay. Now, sometimes people like, if you're like one of the, like a tactile learner, some people like to kind of, we call it the hand thing. We just call it that because we see people do it and they're always trying to hide that they're doing it when I don't know why. Okay, but that's fine. Okay, so they put their hands together pointing in the primary direction. So if it was like north of east, all right, so I'm going to point north, or sorry, north of east, I'm going to point east, and then I'm going to go north of that. There's my triangle. There's where I draw it. Okay, and it works every single time. For me, I just draw it. If something is 30 degrees north of east, I draw a dotted line east. I go 30 degrees north of it, and I've got my triangle drawn. Okay, that's generally how we do it. But if you're a tactile person, sometimes it just makes your brain feel better. Okay, when you do it the way your brain was trained, which is tactile. Okay, so it's just funny on the final exam when people are writing their final exam, they're like doing this and they think there's something embarrassing. Guys, if it works for you, do it. Okay, like it's nothing to be embarrassed about. Okay, so does everyone understand the directions? Because we're going to use compass directions a lot. Okay, all right, so the direction the arrow points represents, or the direction the vector points represents the direction that it's going, and the length of it represents the magnitude. Okay, so this sentence here that's in italics, okay, is important because it's one of the fundamentals of drawing a vector. And then similar on the next slide, okay, we talk about how the length of the arrow is proportional to the magnitude of the vector. Okay, that's the vector drawing rules. Okay, and also make sure you draw your compass right. Okay, anytime you have a question, okay, that involves compass directions, put a compass on there. Okay, I still do that. I still draw a compass when I'm doing compass direction questions, right? And remember that it is never eat soggy wieners, okay, and clockwise around it, okay? Because I sometimes have people reverse the east and the west. Very rarely do they reverse the north and south, but occasionally they reverse the east and west, okay? All right. So this is what you would have done, Science 10, and we've kind of already done, we just have never drawn it this way, okay? When we want to add collinear vectors. All right, so we have these two vectors. The first vector is 275 meters due east. So we're talking about a car that moves 275 meters due east. All right, so that's this first line or arrow here. All right, they've just written it as DAB. We don't generally write it that way. I write on here 275 meters. I put the length on there. Okay, I write the magnitude, 275 meters, and I let the direction of the arrow explain that it's going east. Okay. After that 275 meters due east, the car goes another 125 meters due east from there, right? That's the next vector. All right, notice that I drew the second vector right on the head of the first. Okay, it's like I'm drawing the trip in the order it happens. That's always the way we want to do it. Okay, that's what we mean when we say draw them tail to head. Okay, we put the tail of the next vector on the head of the first, okay, indicating this one happened, and then from there, this happened. And then from there, this happened. All right. The thing that I see people do all the time is when they're drawing a vector diagram, they do this. All right, 275, and then they go. What does that diagram say the object did? That says the object split in half. Part of it went 275 meters east, and part of it went 125 meters east, because there's no way I could do both of these from that position with the same object. Okay, I can't do them both at the same time. One happened after the other, so I always need to reflect that when I draw. The question said the car went 275 meters east, and then it went 125 meters east. Okay, I have to draw it in the order in which it happens, tail to head. All right, everybody understand how to draw those? Okay. All right, so now that I've got that, can I calculate my total displacement? Is it pretty easy? Right. All I have to do is what? just add them together. Yeah, okay, super easy. I just add those two numbers together, right? So it's going to be 400 meters east. Okay, will be my total displacement. All right, so that's how we would add collinear vectors, right? And it's not really any different if I have it like backtrack. Let's say it went 120 or 275 meters to the east and then went 125 meters west. Okay, I still draw the second vector on the head of the first, right? I went 275 this way, then I went back 125. So now instead of adding them, I would subtract, okay? Because this is my change in position. Okay. All right. So, like I say, you guys have done stuff like that. You've just never seen it drawn this way. All right. So all we would do is add them together. So we've already talked about that. Okay. But this is that tail to head thing. Okay. So the two vectors add up. So we place vectors tail to head. That is, the tail of the second vector is placed on the head of the first, and we do that for all vector addition. Okay, questions there? All right. How is this going to change if instead of going this way or this way, now suddenly the next vector goes that way? Where would I draw a line now that represents my total displacement? See a bunch of you doing this. Okay, you're right. Yeah, you would do this. That is, you would draw the line that connects the initial position with the final position, because that's what displacement is, right? It's your change in position from initial position to final position, and that is what that line, which is now the hypotenuse of a right angle triangle, represents. Okay, this line here now represents my total displacement. How do I go about finding out how long that is? Since I now know one side is 275 and one side is 125, a squared plus b squared equals c squared, right? Okay, we use the Greek geek. Okay, Pythagoras is the Greek geek. He spent his whole life studying triangles. Okay, so we would use that to find the length of it. That would give us the magnitude. But this is a vector quantity we're trying to find. How do I find out which way that's pointing? Because I can't just say northeast. That's not specific enough. We already talked about that. How do I find theta? Right, I got to use trigonometry. Right, so I mean, if I had already calculated what d was, I could use any trig function I wanted because I would have all three sides of the triangle. Here's what I caution though. If you screwed that calculation up and then you use that number, will this be right? No. Okay, keep that in mind. I always try to use numbers I was given as often as possible, just in case I, forgot to carry a decimal through or something. Okay, so I always use the numbers I was given. So that would mean I would be using the opposite side and the adjacent side. Which trig function is that? Tan, right? TOA. Tan is opposite over adjacent. That would give me that angle. Okay, so that's where we're headed next. How do we add perpendicular vectors? So we do what you guys just told me. Okay, we draw them tail to head like they show in this diagram. So this would be our 275 meter. This would be our 125 meters. So 275 east, then 125 north gives us that. And then this red line represents the total displacement over the entire trip. All right, and as we said before, we would find this length using Pythagorean theorem. Okay, and then we would use trigonometry in order to get theta. Okay, so trigonometry will tell me 275 squared plus 125 squared, square rooted, will give me 302 meters. So my overall displacement, which is the red line, would be 302 meters long. And then I got to find theta. Okay, theta is going to be, if I'm looking for it, I'm using the opposite and adjacent side. So tan of theta equals opposite over adjacent. If I want to find theta, I bring tan over here, which means I'm doing tan to the -1 or inverse of tan, right? Okay, when you're looking for the angle, so you go theta equals inverse tan of opposite, which was 125, over adjacent, which was 275. Okay, that's how we get theta, all right? And that's going to give us about 24.5 degrees. Now, right here, should I have rounded that number off, or should have I kept everything? Kept it, right? It makes a difference. Also, make sure your calculator's in degree mode right now, okay? So hit the mode button and make sure that degree is highlighted. Especially if you're in math right now, you're gonna be going back and forth between radian and degree all the time. You always need degree in physics, okay? So make sure your calculator's in degree mode or it will give you nonsensical answers, and it's very frustrating. Okay, so I'm gonna go tan to the -1, so inverse tan of 125, the opposite side, divided by the adjacent side, 275, right? That gives me a different answer, okay? Because I rounded that one off, okay? I got 24.5 degrees. When I actually use the number in its entirety, I get 24.4, right? That would mean I would get that question wrong, even though I did most of it right, okay? Because I rounded this off and used it in my tan calculation, I would actually get the question wrong. This is the correct answer here, okay? Sorry, I should show you this instead. 125 divided by 275, okay, gives you, right? I rounded that to 0.455 when it's actually all of this, and that makes a difference in my answer, okay? So we want to keep all of our decimals until the very end. Okay. All right, questions on what we did there? All right, so we're going to have to use our trigonometry muscles a little bit, okay? You probably have not used those recently, okay? So they have atrophied a little bit on you and you will have to get them back in shape. We're going to be using it all the time. Now, as a reminder, okay, you were taught that when you were a kid, SOHCAHTOA, okay? That means that sine of theta is opposite over hypotenuse, okay? Cos of theta is adjacent over hypotenuse, right? And tan of theta is opposite over adjacent. Okay, those are things you'll have to remember when you are using those formulas. Okay, so we'll do a couple of examples here just to kind of review how this works, and then we'll have a look at something tougher. All right, this one's pretty easy. Give this one a try here. Okay, so this one's pretty easy, okay? It is the race to end all races in the most boring town in the world. Because these contestants move forward 10 meters. And then they untie some knots. And then they move forward 5 meters and solve a puzzle. And then they move forward 25 meters to the finish line. All right, now I've got, again, approximately to scale, right? My 5-meter line's about half as long as my 10-meter line. My 25-meter line is about 2.5 times longer than my 10-meter line. I didn't measure them, okay? But I tried to reflect scale as best I could. All right, it's all in the same direction. It's all forward, okay? So my total is going to be 40 meters forward, right? So we solved it using a vector diagram. Questions on that one? Okay. Okay, I want you guys to try question 6 first, and then we'll look at 7 as well. Okay, so try 6 first. I'll give you a few minutes on that one. Okay, so on 6, okay, so we've got our football field here. Okay, and they go to each 10-yard line. So they're going to go to the 10-yard line, and then they're going to go back, and then they're going to go to the 20-yard line, and then they're going to go back, and then they're going to go to the 30-yard line and back. Okay, and then they're going to go, and rather than draw these right on top of it, like a true vector diagram, I'd be drawing these right on top of each other, but would that be easy to see? Right, so in this case, I'm going to spread them out a little bit. Right, so that was the 30-yard line, then okay, 40 and back. I didn't leave myself enough room. Okay, 50 and back, you get the idea. Okay, by the end, their total displacement is 100 meters because they end up at the far end of the field. Okay, so 100 meters downfield, I guess we would have to say, because they don't really tell us. They don't really tell us how far that is, or sorry, what direction that is. Okay, and then how far did they run? Well, we'd have to add them all up, right? So this would be 10, this would be 10, 20, 20, okay, 30, 30, and you just add them all up until you get your total. Okay, again, not caring whether they're forward or backward. Okay, number 7 is a thinker. Okay, it's not really so much a vector diagram question as it's a bit of a math trick. Okay, number 7. Okay, car drives north 500 kilometers. Then it drives 3 sequential displacements south, each of which is 50 kilometers longer than the previous displacement. Okay, the final position of the car is 50 kilometers north. Find the 3 displacements algebraically. Okay, it's a good challenge for you. I would never ask you something like this because it's a math question more than a physics question. Okay, but it's a good challenge. Okay, it's always good to push yourself a little bit. So give that one a try. Okay, we know they went 500 kilometers north, so this was like the first part of the trip, 500 kilometers. Okay, they came back to a point here where they were 50 kilometers north of where they started. So they did this part of the trip in 3 sequential segments. How far is that part of the trip? 450 kilometers. Okay, so these 3 legs add up to 450. And we know that each leg is 50 kilometers longer than the leg before it. Okay, what I don't know is how long the first leg is. So I'm just going to say the first leg is x, because I don't know what it is. Now, how long is the second leg? X plus 50. How long is the third leg? X plus 100. Okay, that's what they told me. Each leg is 50 kilometers longer than the leg before it. The first leg is unknown, the second leg is unknown plus 50, okay, and the next leg is unknown plus 100. Now, I've got all those in a row, okay, and I've got 3 x's here that are added together. So I'm going to bring the 2 numbers that I know back over here. All right, I'm going to go 450 minus 150. So I'm going to have 300 equals x plus x plus x, which is effectively 300 equals 3x. How big is x? 100. All right, so this first leg is 100, okay, then, well, I didn't draw that to scale, 150, and then 200. Yeah? All right, so you can kind of use, the vector diagram a little bit to help you with that one, okay? But for the most part, it was just a math trick. As long as I could isolate the stuff I didn't know, then I'd be able to solve for it. Okay, I want you to try this one. Draw the diagram, okay? Draw all these vectors tail to head, okay, to get your diagram. Then draw your resultant. The resultant is the line that connects the initial position to the final position. That's the line you're trying to find here. All right, I'll give you a few minutes to give that one a try. Okay, so just to help people out here, I'm going to draw the diagram, okay, just so you can see what that diagram looks like. So the first part of this question, she walks 0.8 kilometers south. And then she goes 1.2 kilometers east. And then she goes 0.3 kilometers north. which means my resultant is this line here. Okay, this is my displacement from start to finish. What we're always trying to accomplish with vector addition is to get our resultant in a right angle triangle so that we can do trig. Right? So I can do that if I can draw this actually one of two ways. I can draw that triangle this way, or I can draw it this way. Either way, I will get the same magnitude, but I'll get the same direction from different points of view, all right, depending on how you draw it. Whichever way you draw it is fine. I always try to draw my triangle outside of the diagram so that it doesn't get busy. Okay? All right, I'm going to give you guys a couple more minutes from there and see if you can solve it from there. Okay? So, like I said before, in all vector addition, what we want to end up with is our resultant, okay, our kind of final, connecting our initial to final line, to be in its own right angle triangle. Because from that right angle triangle, I can find its x or horizontal and y vertical components. That is the other two sides of the triangle, right? So if I'm looking at this triangle here that I've drawn, I know that over this whole trip, this person ended up 1.2 kilometers east of where they started from a horizontal perspective. Okay, so we would say that that is the x component of what she did, the horizontal component. But she also ended up how far south? 0.5 kilometers, because she went 0.8 south and then she backtracked 0.3 north at the end. So this side of the triangle here is 0.5 kilometers north. That would be my vertical or y component. Now that I know those two sides, I can figure out everything else about the triangle, including its magnitude and direction. So that's what I need to do now. All right, so I take all the vertical stuff and I add it together. Negative 0.8 plus positive 0.3 gives me negative 0.5. So I know 0.5 south. There was only one trip where she went east and it was 1.2 kilometers. I throw all those together. Okay, so our overall displacement's magnitude, okay, is going to be the square root of 1.2 squared plus 0.5 squared. All right, so the overall displacement is 1.3 kilometers. Okay, so that's the magnitude. And then I have to find the direction. I have all three sides. I could use any trig function I wanted, but I like tan. It's my favorite. So I'm going to use tan. I'm going to use 0.5 over 1.2 to get this angle here. All right, so we'll go tan to the minus 1 of 0.5 divided by 1.2. So that's opposite over adjacent. Whoop, I put the 2 in, there it is. Okay, so that angle is going to be, we only have two significant figures here, so it'll be 23 degrees. Okay, and that's going to be which direction? South of east, exactly. Okay, my angle arc touches due east, and I am south of that, so I am south of east. So we just write S of E, south of east. All right, now I have my total displacement. It's 1.3 kilometers at 23 degrees south of east. Now, I would also accept as correct, because it's equally correct, if you drew the triangle this way, you would have found this angle. Okay, and that angle would be 67 degrees east of south. Okay, if you drew the triangle the other way. Okay, both of those are equally correct. They're just from different points of view. Here's the thing though, guys. In drawing these triangles, so I'm just going to erase this second one here, okay? I oftentimes have people who solve for the wrong angle. So they're doing this triangle, and then for some reason they solve for that. Okay? And then they tell me that by going east and south, the person ends up north of west. Okay, so you always have to make sure that your answer makes sense with your diagram. Okay, this is where you started. You might want to even label that initial position, final position. Okay, you don't want to find the direction that leads you back to the start. You want to find the direction that leads you to the finish from the start. So I always say, if you're confused, circle your initial point, and there's the angle you need to find. Okay, whatever part of that circle goes into your triangle, that's the angle you have to find. Circle your initial point. All right. Okay, questions on that? So what we're always trying to do is get a right angle triangle containing our final resultant. Nope. We already did one like that. Okay. Here's where we're headed. I want you to copy this question down, and we're going to walk through it, but this is where we're headed. First step in solving any vector addition question is to draw the vector diagram. That is essentially your givens for the question. All right, and we want to draw it in the order the question says it happens. So the first part of this trip is 10 kilometers at 30 degrees south of east. So I need a line that is going due east to act as a reference for me, okay? And I'm going to go 30 degrees south of that. Okay, and this is 10 kilometers long. This side is my horizontal component, okay? So the part that goes along the x-axis. And this is my vertical component. Okay? On this diagram, they represent east, west, and north, south. The second part of this trip is 3 kilometers at 10 degrees east of north. Okay, so from this one, that's where I have to draw the next vector. Now my reference direction is north. Okay, so I'm going to use this. I'm actually going to draw another dotted line right beside it. Okay, and I'm going to go 10 degrees east of that. Okay, this is 3 kilometers. This would be my x, this would be my y, and this is 10 degrees in here. Okay, so those are my two vectors drawn tail to head. This one happened first, the black one, then the green one. Okay, so a line that represents this hiker's total displacement would go from start to finish. And it would also have a right angle triangle. Now, that blue dotted line should go right over top of the black one. I'm just not doing it that way because it gets too busy. Okay, this would be x, and this would be y. This would be theta, and this would be my total displacement. Okay. So I do have a right angle triangle for my resultant. Okay, and that's what I need. But if I'm going to calculate what D is, I need to know what its two sides are. Agreed? Okay, I need to know what blue X and blue Y add up to. How am I going to find that? Because I don't know any part of that triangle. Do I know some parts of the other two triangles? Okay, how many pieces of information do you need about a triangle to figure everything out about it? 2. A side and an angle, 2 sides, okay? Something like that. You need 2 pieces of information, right? And in this case, I have a side and an angle. In fact, I have the hypotenuse and an angle for both of those vectors. So using that, can I find out what their x's and y's are? I can. Okay, this is where trigonometry really kicks in to what we're doing. Okay, if I want to calculate black x, okay, black x is the adjacent side of my 10-kilometer triangle, right? Because it's against the 30-degree angle, so it's the adjacent side, which would mean black y would be the opposite side. Okay? And I can use trigonometry now to find out what those are. Can I do the same thing for the green triangle? Okay, so let's say I found out what all the green x and green y are, black x and black y are. I find those out. Can they help me find blue x and blue y? Yeah, because blue x is black x plus green x, right? If I put the black x and the green x together, they would equal blue x. And black y plus, okay, green y, one would be negative, would add up to blue y. Okay, everybody with me there? So I got to find a whole bunch of sides so that I can find the end result. Okay, we call this vector component addition because I'm finding the vector components. I'm finding the horizontal x components and the y components, and I'm adding them together. Okay? I'm not actually adding the two parts that I know, the 10 and the 3. I'm not adding those together. They're in different directions, but they're made up of things that are the same. They're made up of east-west components and north-south components. If I can find those I can add together because they're collinear. Okay? Everyone all right with where I'm going with that? Okay, so just kind of follow along with me here. This is the first time you're going to do one like this, but trust me, okay, within a week or so, this will be second nature. All right, we're going to spend a lot of time practicing it, but it's a lot of steps. The good news is it's the same steps every time you do one. All right, so once you learn the steps, it's just a matter of doing them faster. Okay. All right, so what I'm going to do first is I'm going to find the components of the black triangle. Okay, so as we said, black x, which is, okay, this one right here, is the adjacent side to the 30-degree angle. And I know the hypotenuse of that triangle. Okay, so I can calculate x using cos. Okay, the cos of 30 degrees, the angle in there, is equal to x over 10, the hypotenuse, right? Adjacent over hypotenuse is cos. Everyone follow me there? Okay, so if I want to get x, what do I have to do with the 10? Okay, cos of 30 equals x divided by 10. I want to find x, what do I do with the 10? Multiply it over to the other side. All right, so to get x then, x is going to equal the cos of 30 times 10, the hypotenuse. That will give me x. Okay, well, I already wrote that was x. Okay, so in my calculator, I'm just going to do exactly that. Okay, I'm going to go cos of 30, okay, 30 times 10. Okay, so that side's going to be 8.66025, and I want to keep all those decimals. I'm not going to write them all down because that'd take forever, okay, but I want to keep all of those. So 8.660. Okay, and that's going to be kilometers, and that is, which way is x pointing? East. Okay, then I want to find this side. Okay, I want to find black y. Okay, well, black y is the opposite side, so I'm going to do a similar thing here, except instead of using cos, I'm going to use sine, because it finds the opposite side. Okay, so I'm going to go sine of 30 degrees times 10. Okay, and that'll be 5. And which way is that? Which way is y pointing? South, right? If we go back to the original question here, okay, they went 30 degrees south of east. That means the y component is south, okay? South. No one's like impressed that I did that trigonometry in my head. Sine of 30 times 10 is 5. Don't be impressed. The sine of 30 is 0.5. That's why I use 30 degrees all the time. Okay, I can remember that one. All right, so now I've found out two sides of this triangle. I know that black x is 8.660 kilometers, and I know that black y is 5.0 kilometers. So I know some of the parts of this diagram. Now I need to do the same thing with the green triangle. Okay, in the green triangle, x is the opposite side. So in this one I used cos to find x, but in the next one I'm going to use sine, okay, because I'm finding the opposite side with the hypotenuse. Okay, so x in this one is going to be the sine of 10 degrees this time, times 3 kilometers. All right, so that side is going to be very small. Okay, it's only 0.5209 kilometers. Okay, and then I need to find y. So in other words, I need to look at now how far north did they come back on this 3 kilometer part. I just found out how much further east they went. Now I'm going to find out how much north did they come back, because they started out going south and then they came back north, and I got to figure out how much. That's the adjacent side on this one. So I'm going to go cos of 10 times 3. All right, so they're coming back 2.954 kilometers. That one's north, that one's east. Okay. Okay, so now I can figure out how far east they go in total and how far north-south they go in total. Agreed? Because I know how far east they went in the first one and how far east they went in the second one. And I know how far south they went in the first one and how far north they went in the second. So I can figure out what those totals are at this point. Everyone okay with that? Okay. So effectively now, I want to find this blue triangle, okay, by adding the two y's together, even though one's south and one's north, one of them will be negative, okay, and adding the two x's together, which both point east. All right, so blue x is going to be the 8.660 kilometers east we went in the first one, plus the 0.5209 kilometers east we went in the second one. Okay, so we got okay, so we got, I'm going to try and keep all my decimals here, 8.660254 plus our 0.5209. Okay, so we got 9.189, well, I'll say 9.189, and I'll put in all the stuff here afterwards. Okay, kilometers, and that's east. I need to do the same thing with the two y's, except that one of them is south and one of them is north. Okay, so I'm going to say that the first y is negative. Okay, so I'm going to go negative 5 kilometers, okay, plus 2.954 kilometers, and that'll give me how far south I end up. So negative 5 plus 2.954423.259. Okay, so in total then they go 2.046 kilometers south. Okay, so what I've just found out is this one and this one. Okay, now I know the sides of my total displacements triangle. And now I can use them to find out what the magnitude is using Pythagoras, just like we did with the girl in the camping trip, and trigonometry to find the angle, just like we did with her question. Okay, So when it comes right down to it, yes, there were way more steps and a lot more trigonometry. But in the end, we got it down to a right angle triangle containing my final displacement. Okay, once I have those sides, Pythagoras and trig, and I'm done. Okay, but yes, there's a lot more trig to get there in a question like this. All right, so when you first start trying these on your own, like the first time you do this, it'll probably take you like 20 minutes to do the first question. All right, even like for me, I'm slowing it down and walking it through, right? And we've been doing this for probably about 10 or 12 minutes already. Okay, when you get better at this, a question like this will take you 7 minutes or less, okay, depending on how quick you can type stuff in. All right, so now I have the two blue ones, okay? Now I'm going to find D, which is the hypotenuse or the magnitude of the displacement for this question, right? So D is going to equal the square root of, okay, these two numbers here. So 9.189 squared plus 2.046 squared. And I want to keep all my decimals again all the way through. Okay, I know that on some of these calculators you can just like select one of these numbers. That's super convenient. For some reason that doesn't work on this one, so I always have to go back and type it all in manually. Okay, so we've got, right, the square root of our 9.189, so we got 9.189 699.268 squared, okay, plus 2.045576741 squared. Okay, so my overall displacement is 9.4, and I only have two significant figures here, so 9.4 kilometers. Okay, so that's how long this arrow is, which goes from my final position, or sorry, my initial position to my final position. And now I need to know what direction is that, right? So again, I'm going to use trigonometry there, and I'm going to find theta, okay, by going tan to the minus 1 of the opposite side, which for me is y. So that's the 2.046 divided by 9.189. And that'll give me my angle. Oh, whoops, you're right. Sorry, that's my adjacent side. Good eye. 2.0476741 divided by 9.1899699.368. Okay, so the angle then comes out to 13 degrees, because again, I only have two significant figures here, okay, is going to be 13 degrees. Which direction? According to the diagram that I drew here, which direction is this pointing? South of east. Yep. Yes. Yep. Okay. 9.4 kilometers at 13 degrees south of east. Now, okay, if you'd have drawn the triangle another way, okay, yes, there is another answer, okay, and it would be 77 degrees east of south if you drew the triangle the other way, right? But you probably didn't because you probably drew what I drew up here. All right, that's where we're headed, okay? Vector component addition, okay? It's triangles, 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 okay? If you don't like trigonometry, you better get out now, because it's going to be nothing but trigonometry for the next few weeks. All right, and it's going to be trigonometry in Unit 2 when we're dealing with forces, because we got to add them in the same way. Okay, if you got two things pushing on the same box, you got to add the forces like this. All right, it's exactly the same. All vector quantities are added the same way. Right, it takes some practice, but once you practice this, you'll realize it's always the same steps with different numbers. Okay, but it is always the same steps. Okay, and the steps are like this, guys. You'll want to write this down. Okay, vector component addition steps. Step 1, Okay? Draw each vector, okay, with its x and y components. Right? So that's step one. For that last question, that was when I did this. Okay, so that was the first one, and then I drew the second one on the head of that. So I went like this, okay, and this was x and this was y. I know that's kind of small, but okay, you've seen the diagram already. Okay, that's your vector diagram. So drawing your vector diagram means draw each vector with its x and y components. Okay. Oh, that looks like a P. Draw, draw. Draw your resultant. Okay, we always call it a resultant, but the resultant can represent different things. In the question we did, it represented displacement. Right? But if I was adding two forces together, it would represent the net force. Okay, it just depends on what vector quantities are being added. We always call it the resultant. Okay, so then the second step, draw your resultant. That was when I did this and connected the beginning of the diagram to the end of the diagram and showed its x and y components. So draw your resultant with x and y components. Components. Boy, I'm having trouble spelling today. Now, if you find that a diagram like that is too busy for you, okay, that's fine. Some people don't like to see that because it's all in one place. I like everything all in one place because that's how my mind works, okay? But if you don't like that, you can draw these triangles all separately as well, and the question will still work because mathematically you're going to do the same thing, right? We call that the separate triangle method because the triangles are separate. It fits, right? Okay, so you could draw it like this. Okay, you got your 10 kilometer, you got your angle, you got your x and your y. Okay, then you draw your other one here, but completely separate. Okay, and then once you've calculated those, then you add them up and you can't draw your resultant until you're done. Okay, you wouldn't be able to draw what this looks like until you know what blue x is and what blue y is. You wouldn't be able to draw it till the end. For me, that's unsettling. I need to know where I'm headed. Okay, but some people it's too busy and this works better for them. Whichever way works better for you. Okay, so draw your resultant with your x and y components. Step 3. Solve for all the x and y components. Okay, and that was what we did when I found black x and then I found black y. Okay, it was all the trig that we did up here. Okay, all of this stuff. Okay, and with the green line as well. Okay, that was finding all the x and y components. Okay, that's using all your trig. Okay, so once you've found all the x and y components, okay, okay, then you'll add all the x's together and all the y's together to get your resultants, x and y. Okay, that was when I added when I added black x and green x, and then I got blue x. Okay, I added black y and green y, and then I got blue y. Right, so that's what I mean by that step. Okay, so then we used Pythagorean theorem with blue x and blue y to figure out what our hypotenuse was, what our resultant's magnitude was. That was how far was the overall displacement. Okay, sixth step. Okay, it's going to sound a lot like this one. Okay, use the resultant's x and y, that was blue x and y in the example, in order to find the resultant's direction or vector. And then you're done. It's always the same 6 steps. Okay, it's always the same 6 steps. Draw the diagram, find all the x's and y's, okay, use the x's and y's to get the resultant, okay, use them to get the vector, and you're done. Okay, it's always the same steps. It's going to take you a while to practice those steps, but it is always the same steps. Even if I was to give you a question where you had 4 vectors adding up to some total, okay, you would just have to find a lot more x's and y's in a question like that. I'm not going to do that on a quiz or a test, okay, because it doesn't tell me how well you can do it. It tells me how fast you can do it, okay? And while that's somewhat important, it's not the primary concern of mine, okay? My primary concern is, can you do it? Right? So I will not ask you on a test a vector addition question that will take you 40 minutes to complete, okay? That's not practical, right? I'll ask you one easier than that. All right, that's a lot to take in one day. So we will leave it there. And tomorrow we're going to start out with you trying one of these. Oh, no, sorry. We'll start with a quiz first. Then we'll try one of these. The quiz will be on acceleration. Okay, so we'll have one more acceleration quiz. I'll post that at 3:30.